and Ecole Normale Supérieure de Paris, who will talk about sharpness, restart, and completeness and performance.
Thank you, and first thank you to the organizers for the invitation. I should start by saying that this is joint work with Vincent Roulet, who just started at the University of Washington, and Nicolas Boumal, who's at Princeton now. So I think you may have heard the general story earlier this week. The idea is that there's a clear empirical link between statistical performance and computational complexity. So I believe, I wasn't there, but I believe Michael Jordan probably spent a bit of time talking about this earlier this week. In practice, if you don't have as many samples, typically you need to do detection, for example, you need an estimator that has higher complexity. If you have more sample, on the other hand, typically a much simpler procedure is going to work. Okay, and so you have this trade-off curve between computational complexity and statistical performance, and most of the time all we have now is a few points on this curve, but we don't really have a precise idea of the mechanism that structures this trade-off. Okay, so there's nothing explaining why we have this trade-off between these two quantities, but empirically it's something that's verified in a very robust way. Okay? And part of the problem is that the quantities describing computational complexity don't really make any statistical sense. It's of course hard to define what we mean by statistical sense, but they don't really tell you what's going on in the data from a statistical point of view, and are not able to detect the computational complexity of actual statistical problems based on the data itself. And so in this vein, and to illustrate this point, I'll start with two minor enigmas this morning that are seemingly unrelated, but we'll see have a common solution and sort of at least highlight a possible answer for compressed tensor problems. So the first enigma dates back from a paper by Dono and Seg in 2008 called Fast Solution of L1 Norm Minimization Problems when the solution may be sparse. And you may have seen these graphs before, right? So we have the phase transition curve here in dashed red line. And then we have these shaded areas of gray, increasing shades of gray. And what typically happens in these graphs is that the darkness of the points here reflects the probability of recovery. Here the graph is a little bit different. The red curve is indeed the phase transition frontier. Okay, below this one, lasso, for example, will recover a sparse solution with very high probability. Above it will fail. So that's the red curve. But the shades of gray here denote computational complexity. So the amount of time it took the lasso, in this case it's the homotopy solver, to get to the solution, right? So we have a statistical phase transition around this curve in red, but we have a computational phase transition in the shades of gray. And this graph is here because the two very precisely match, right? The difference between these two plots is a different kind of normalization. This here is normalized with respect to the cost of solving the corresponding least squares problem, and this is normalized with respect to the dimension. So the shades of gray differ, but the phase transition is still there, right? It's just scaling. It's important because essentially this is the iteration complexity, the number of iterations of the algorithm that you require, but not the floating point complexity, which is essentially CPU time. And this is closer to a normalized version of CPU time, but that's a detail. Okay, so that's our first enigma today. Why do these two curves match so precisely? There's a phase transition in computational complexity precisely on the frontier where the phase transition occurs for statistical performance. First enigma. Second one, seemingly unrelated. Templates for convex problems with applications to sparse signal recovery. This is the paper corresponding to a package called TFOX that was developed by Stephen Becker around 2010 or so. It's now starting to get integrated into CVX, etc., and it allows you to write efficient codes for large-scale compressed sensing, matrix completion, etc., using first-order methods without reinventing the wheel every time. So all the building blocks you need to write a large-scale code for L1 minimization, for example, are there, right? And so Stephen Becker, who's a very thorough guy, went and tried every possible trick in the book to speed up first-order methods, and one of the things that worked best was restart. Okay, so you take the usual method you're using for L1 minimization, say, first order, and periodically you dump everything and restart the method from scratch at the current point. Okay, that works quite well, and it's illustrated on the graph taken from their paper on the right here. The blue and green curves are the ones you get by running the algorithm without restart. Okay, and you get this sublinear convergence. And the other three curves are the ones you get by using the same method without changing anything, but restarting them periodically. And I don't have to convince you, I think that there's a pretty significant difference in performance, right? And we don't really have, or at least we didn't really have an explanation for why the performance is so good. This was on the Danzig selector, so it's a compressed sensing problem, and clearly here restarting makes a huge difference in terms of performance. Okay, so two seemingly unrelated enigmas, and what we're going to do today is essentially kill two birds with one stone, or whatever politically correct term stands for birds these days. Let's say baby seals, and essentially see that sharpness is actually the reason why restart works, and that sharpness is something that occurs naturally in compressed sensing problems. Okay? But before going there and describing those results, I should probably start by saying a few words by what we mean by sharpness. This is not such a common assumption in practice, so I'll spend a little bit of time essentially discussing optimization and complexity issues around optimization, and then we'll see that the sharpness assumption I'm discussing here is something that occurs naturally in compressed sensing problems, right? So this is a perfectly generic optimization problem. We're minimizing a convex function f over a set Q, and when you have a problem like this and you want to use an efficient method, typically you rely on a smoothness assumption on the gradient. And so here we're going to assume that the gradient is Holder smooth. Okay? But we're going to make an additional assumption, which is sharpness, that the minimum of the function is sharp, and we're going to quantify this sharpness using the exponent r, and assume that the difference between the function value and its minimum is an upper bound on the distance between the point x and the set of minimizers to the power r with a certain coefficient mu, right? And that's important. This will be a local property. Not always, but at least here we're going to assume this holds locally. So that's sharpness, and we'll see that this is the key to explain the behavior of these methods when we restart them. And this was well known, at least in a particular case that is quite classical, which is strong convexity. Strong convexity is a particular case of sharpness with r equals to 2. Okay, when you have strong convexity, this holds. And if the function is also smooth, but you ignore strong convexity and run an optimal first order method without taking into account the strong convexity of the method, you get this upper bound on the difference between the function value at the point x and f star. So this is just the complexity bound for an optimal first order method for smooth minimization, and this is strong convexity. It doesn't take a lot of thinking to realize that you need to put these two things together. When you do that, you get this inequality between the function values, comparing the difference with the minimum at the initial point and the difference with the minimum after tk iterations. And what you see is that you have this constant decrease in function values. So every time you restart, you're guaranteed, with a fixed number of iterations, you're guaranteed a fixed decrease, linear decrease in the function values, and so you get linear convergence of the restarted iterations. Of course, you're making a lot of inner iterations, so you have to account for all of these to get a global complexity bound, but in the strongly convex case, this tells you that restarting a method, an optimal method that ignores strong convexity periodically with a constant number of iterations for a strongly convex function will give you back linear convergence. So in the strongly convex case, it's pretty obvious why restarting works. And the question is now, does this hold in a much broader set of scenarios?
Now,
Yes.
clarify, if the function happens not to be strong convex, then you would get back to the non-accelerated rate. Right?
That's what follows. So if you wait a few slides, you can do better. Restarting also works when you're not strongly convex, but you're sharp enough. And so that's my point, the point that follows. So, sharpness is nice, at least in the strongly convex case, and we'll see that what happens in the strongly convex case can be generalized to a broader set of scenarios. But there's something special about this sharpness assumption. Smoothness is classical. Sharpness is a less classical assumption, but that's a bit surprising because, in fact, sharpness almost always holds. And this dates back, it's easy to see in dimension 1 because you just do a Taylor expansion and the first non-zero exponent gives you the sharpness bound. But in a multidimensional setting, it's a much harder result. And it dates back for real analytic functions to Lojasievicz in the 60s, but it was generalized to much broader class of non-smooth functions by Lojasievicz in the 90s and Bolt and co-authors in 2007 or so. So essentially what these results tells you, their result concerns all subanalytic functions, and all the functions you care about turn out to be subanalytic, right? So that's all for now. So essentially all functions are sharp except some pathological ones. And this was pretty broadly studied in the optimization literature under various names. And none of these names are particularly, there's no unified term, and that's probably why the assumption is not more broadly known. And it's usually called error bound. And unfortunately, error bound is not a very discriminative keyword. And so that's why in this talk at least, I'm using sharpness for functions that may not be sharp. So we'll say that strongly convex functions are sharp, even though there's nothing really pointy here. It's just because sharpness is a better keyword for search than error bound. So my apologies. But in practice, the real important news here is that most functions turn out to be sharp, except pathological ones, such as the exponential of -1/x². If you're trying to minimize this, you can't assume sharpness, but otherwise, essentially, you're always sharp with a varying degree of sharpness controlled by an exponent r, and typically you don't know r, and you don't know mu. But sharpness will hold. So a few things we can say in addition to that. So if you assume that the gradient is Hölder, you have an upper bound on the difference between the function value and the minimum. Sharpness gives you the opposite inequality. That creates a link between, since those two bounds must hold locally, that creates a relationship between the exponents related to the gradient and sharpness. So you need S smaller than R. And you can define these two condition numbers here, kappa and tau. Kappa essentially generalizes the classical condition number for optimization, so the ratio between the smoothness of the gradient and the strong convexity parameter. So that's the usual condition number you're used to. And tau is a normalized version of the sharpness coefficient. So it's the ratio between the smoothness of the upper bound and the smoothness of the lower bound. And we see that tau is the critical parameter that would control the amount of acceleration you get by restarting. So tau is between 0 and 1, and it's the main parameter controlling acceleration. So sharpness and restart schemes were studied in the past, and probably the main reference here is a paper, a sort of fairly obscure paper by Nemiowski and Nesterov in 1985, it's literally obscure because, well, one, it's written in Russian, and second, when you print it, the scan is so bad that you don't see the exponents, which for a paper about complexity is just a little bit tricky. But you can make up for the gaps. And they study the impact of restart on sharp functions, but if their paper sort of predates all the results about Lojasievicz, etc., and so the importance of the sharpness assumption was not recognized at the time. That's probably why the paper remained obscure, in addition to the scanning issues. But so they essentially work out the complexity of the impact of restart on sharp functions, and show that you get optimal complexity in this case. I'll come back to this. But then several heuristics for restart were studied recently in other settings, in particular compressed sensing, but these results are mostly empirical. And a more recent paper studying the robustness of restart schemes by Vercock and Chu in 2016 applied to the strongly convex case. And there's also a paper on matrix games showing linear convergence, etc. So restart was around there, but the link between restart and sharpness was really only established by Nemirovsky and Nesterov. But this was not really, didn't get the publicity it deserved, probably because the sharpness assumption was not that well known at the time. Okay, so what do I mean? What are we going to mean when we say restarting a method? Well, we're going to take an algorithm A, start at a certain initial iterate x0, run algorithm A for tk iterations, and restart the method at xk, forgetting everything we've computed in the method. If you think about it for a moment, this may make sense. Optimal methods for optimization typically accumulate a certain amount of information. That's what makes them optimal. But at a certain point, when you reach a point close to the optimum, this information becomes a little bit of a nuisance, right? Because it's old and irrelevant. And so dumping it actually improves performance. That's the hand-waving way of explaining why restart works. And the non-hand-waving way involves essentially saying that we're going to decide that we restart with a geometrically increasing number of inner optimizations and steps to make sure that the difference between the function value at the current point and the minimum decreases geometrically for at each outer iteration. And what we'll see is that considering restart schemes of this type is enough to get us optimal complexity. So the first result we can get about this restart scheme is that when tau is equal to 0, and remember that tau is essentially the parameter that controls how much sharpness you're getting at the optimum, you get linear convergence, and the bound actually follows the rate of linear convergence is the classical accelerated rate given by this new condition number kappa. But this matches the classical accelerated linear rate you get for strongly convex functions, for example. And going back to your earlier question, when tau is strictly positive, so you're not in the strongly convex case, but you're in something in between because you don't get the same amount of sharpness, the complexity is now proportional to the inverse of the number of iterations to the power 2 divided by tau. And remember that tau is between 0 and 1. So when tau is equal to 1, you don't get any benefit. There's no speed up over the optimal complexity bound. But when tau is a bit smaller, you're going actually faster than the optimal bound for smooth minimization. And that's, of course, because you're breaking the black box. You're making this additional sharpness assumption. And this sharpness assumption allows you to go faster, and you go faster by restarting. Yes?
Maybe you missed it, but what algorithm are you using here? Like you say, just
oh, I'm using an algorithm that reaches the optimal complexity of smooth minimization. So typically Nesterov's method, but it could be Fista or whatever. All you need is the classical complexity bound for accelerated first order minimization. Yes?
Can you talk about adaptivity here a little bit?
If you wait one slide, I'm going to do exactly that.
I'm in a bit of a hurry.
Well, then I can skip the... Okay, so here it is. All right? So basically what Nesterov and Imirovsky did is exactly what we did here. The formulation is slightly different, but that's the idea. But of course, in practice, especially since this is local and you don't know X star, etc., the problem, you don't know the exponent r, mu, etc., so you don't know how to specify your restart strategy. And so we need to make these restart schemes adaptive if we want sharpness to be useful, right? And this in particular will solve the robustness problem for accelerated methods in the strongly convex case. Because typically we don't have good bounds on the strong convexity parameter. Local strong convexity is much better. And so restarting turns out to be a better way of exploiting strong convexity or sharpness in the general case. And so it turns out that a sort of very brutal argument works. And if you do a log-sized grid search on the restart scheme parameters, you only pay a factor 4 in terms of complexity. And so you're only a factor 4 away from the optimal bound, accelerated bound, using optimal restart schemes if you do log squared n search or experiments. So the cost of the adaptation here is just a polylog. So this is very brutal, but it tells you that essentially what people noticed earlier empirically, which is that these restart schemes are fairly robust. And if you misspecify them, but not too badly, you're getting optimal performance. So essentially, there's enough robustness so that adaptation is not a problem, right? So that's true in the case when S is equal to 2. It's not true when S is different from 2. So the generic Hölder case is trickier, and we don't have a good solution for that. That's because, in particular, in this case, the complexity bound you get from optimal methods are slightly different, and we don't get the same kind of performance bounds, etc. I won't go into details, but essentially our adaptation result applies only to the case where S is equal to 2. Okay, so the traditional smooth gradient assumption. So that's the classical case, so it's no big deal. Most of the problems we care about turn out to satisfy this assumption, but there's still an open question on what to do when S is not equal to 2. So that's it for the optimization part. The message here is that for most problems, you have some degree of sharpness, and you can actually exploit this sharpness by restarting your method. And it turns out that restart is adaptive enough to get you optimal complexity and improve performance over the optimal complexity bounds that ignore sharpness, right? So now what's the link with compressed sensing performance? Well, easy enough. We'll see that it's a very simple argument. So this probably looks familiar to all of you, but just in case, we're focusing now on sparse recovery, the constrained version. So we're minimizing the L1 norm, so trying to find a sparse solution to a linear system by minimizing the L1 norm. And so there's a galaxy of conditions for recovery. Sarah, who should be in the room somewhere, is the specialist here and has this beautiful graph linking all these conditions. But one of them is called the null space property, and basically ensures that the null space of the matrix A does not contain sparse vectors, but does so in a soft way. So it's going to measure the L1 norm of the vector Z in the null space of A, restricted to a support set S. And if this inequality between the L1 norm of Z on S and the L1 norm of Z on its complement holds for any support S of a certain size, then we say that the null space property holds with coefficient alpha for cardinality S, where S is the size of S, surprisingly enough. So that's the null space property. And it turns out that what we need to show to get sharpness for sparse recovery problems is this inequality. And the null space property is enough to give us precisely this inequality for compressed sensing problems. Okay, so given a coding matrix A satisfying the null space property at order S with constant alpha, if the original signal x star is S sparse, then for any vector x in the space, the space of the feasible set, so the space of vectors satisfying Ax is equal to B, we have this sharpness bound on the objective of the L1 minimization problem. And the sharpness coefficient, so the exponent is 1, but it's written in terms of the L1 norm, and that's going to be important later on. And the sharpness coefficient is alpha minus 1 divided by alpha plus 1. Yes?
So isn't it sufficient for this to have the null space property on the support of X star? Null space properties for every S.
Maybe I should check. You're probably right. So yes, probably. But so here basically null space property gives you sharpness with the sharpness coefficient directly derived from the null space property coefficient, right? And so that's important because we have a good estimate on alpha, and so since the sharpness defines complexity, we start to get a link between compressed sensing performance and complexity. Okay, that link is going to be the sharpness coefficient, right? And so once we have this sharpness bound, what we're going to do is we're going to restart Nesta in this case, which is an optimal first order method for solving the kind of problem, the sparse recovery problem I just detailed. Okay, so Nesta is an algorithm by Becker and co-authors dating back from 2011. And we're going to restart Nesta with geometrically increasing precision targets, right? So the restart strategies are slightly different in some cases. For Nesta, you need to specify the target precision when you run the method. And so here we're going to assume that the target precisions are controlled at each outer iteration, follow this geometric sequence and are controlled by this parameter rho. And the question is, can we find a rho that gives us optimal complexity? But we have only one parameter to set, right? And the main result, making bridging these results on restart on one side and complexity, and the results on sparse recovery on the other, is this one, which says that if you have a Gaussian design matrix A and a signal X star with sparsity S smaller than n divided by log P, then the optimal restart scheme outputs a point y hat such that the suboptimality of y hat converges linearly. And so you forget for a minute this term here, which is a bit artificial and looks pretty bad. What we really care about is this coefficient here. And what this tells you is that when the oversampling ratio n over s increases, okay, you're getting more samples for signal support of constant size s. The problem should become easier. And what this shows here is that indeed the problem does become easier as you get more samples and the iteration complexity decreases. This square root of p here is pretty ugly, but it's there because Nesta is an Euclidean method for a problem that has an L1 geometry. So that's bad, and this is something we should be able to fix. We haven't done so yet, but it's likely that the square root of p can be dropped. I know you're unhappy about this. You look unhappy. It shouldn't be there, but but what we really care about is this thing here. And you see that in practice we get the performance benefit we hope for, but it's just on paper this is clearly not as tight as it should be, right?
It's fairly common to see results like that in complexity fix for compressive sensing, right?
Mm-hmm.
There's only one result I know that gets rid of that, which is the
square root of p, you mean?
Yeah.
Yes, yes, yes.
Agarwal, Negabon, Wainwright paper. That's the only one I know that really gets rid of it.
I haven't dug far enough to get a precise answer, but you need smoothing. So there are two conflicting aspects, and we can probably talk about this at the end, but basically you're doing L1, so you need smoothing. If you do smoothing, you're back to L2, but if you're back to L2, then you lose the square root of p and you're in trouble. So there are the conflicting things, and it may be the case that this is something you cannot drop, but I hope at least, it's wishful thinking, but I hope this is sort of spurious. Okay? But what we care about here, and the main story here, is the link between the oversampling ratio and the convergence rate. The more data you have, the better conditioned your problem is, the faster it will converge, right? So this is true, this is spelled out for sparse recovery, L1 recovery, but it directly generalizes to, or mostly directly generalizes to other decomposer norms, matrix completion, etc. And I do have a bit of time to talk about a similar result involving Renegard's condition number. So I won't go into detail, but I'm happy to talk about it offline. So when you see the initial plot on the phase transition, so you have the border, the red curve where suddenly sparse recovery starts to happen, and the shades of gray on both sides. And what you see is that the complexity increases as you get near the transition. And if you've done a bit of optimization, inter-point methods, etc., on problems that are nearly feasible or nearly infeasible, you know that this is typically a conditioning phenomenon. So optimization problems turn out to be easy to solve when they're well conditioned, and the conditioning from an optimization is sometimes defined in terms of Renegard's condition number, which generalizes the classical condition number people consider for linear systems. And it does so by measuring distance to infeasibility. And what you can show is that typically for most of the optimization problems, the complexity increases as the distance to feasibility, or infeasibility, it's symmetric, decreases. Okay? So if your problem is nearly infeasible or nearly feasible, it's going to be expensive. If your problem is clearly feasible or clearly infeasible, it's going to be cheap. And we see exactly the same thing here, right? So the complexity gets higher as we approach the phase transition. And so here we did everything, we sort of highlighted this phenomenon using a condition number that arguably is the oversampling ratio. But you can do so a little bit more explicitly using the classical condition number for optimization problems coming from Renegard's work. And if you do that, what you can show is that there's an explicit link between Renegard's condition number for sparse recovery problems and cone-restricted eigenvalues. So we're not making a link between the null space property and sharpness. Now, this time, you can get a similar picture by linking cone-restricted eigenvalues and Renegard's condition number for sparse recovery problems. But you get the same picture. And the message is the same, it's just the techniques are completely different. If your problem is well conditioned from a statistical point of view, so you have way enough samples to recover or way too few samples to hope to get anything, your problem is going to be easy. If you're near the sparse recovery border, the problem is going to be hard. And that's a conditioning statement, right? So that's it. And again, the details here are in the paper. It's a little bit less explicit and direct, and so it's another story, basically. And so just to show you that this is actually where we care about numerical performance, so let's look at a few numerical examples to see how much difference this actually makes. Okay, and we're going to do so on classical sparse recovery problems, so in the constrained version, and on completely standard examples, random design matrix with IID Gaussian coefficients. We are normalizing it so that it fits Nesta's format, and we generate observations starting from a sparse vector X star that is S sparse and whose non-zero coefficients are all ones. So it's a fairly canonical set of results. And so the first plot actually shows you the benefit of restarting. So this is what you get by running Nesta with a low precision target here. And this is what you get by running Nesta with a high precision target without restart. So the reason why setting a high precision target slows down the method is because you're going to get less smoothing if you set a high precision target, and less smoothing will mean a slower convergence. So there is a difference in performance if you set higher precision goals, and this is reflected in this plot. And now the two red plots denote the performance of the best restart scheme. So you restart Nesta using the optimal restart schedule, and you get this. But of course, in practice, you don't know what the optimal restart schedule should be, so you do this log scale grid search. And when you do that and you factor in the cost of the search, this is the complexity you get, right? So it's still better in this case. So restarting, even if you have to look for the optimal strategy by brute force, essentially, is still beneficial from a numerical point of view. But in fact, this is, again, as I said, restarting is something people have been using for a while, and Nesta actually includes a restarting heuristic. So they don't really have a proof of the benefit of restarting, but they do have a strategy that works well. And so in some cases, they call it continuation, but it's the same spirit. And in some cases, their strategy actually performs better than the optimal geometrically increasing scheme I detailed here. It does so a little bit adaptively. I don't exactly remember the details, but you can get better convergence than the one I just detailed. Okay, and so again here the solid red line is the best, the Oracle restart scheme. The dashed red line is the performance of restart when you have to search, including the cost of searching for the best restart scheme. And the blue plot here is what you get by running Nesta with the given continuation scheme, right? Probably a bit more important here. This is the complexity of the best restart scheme found by grid search for increasing values of the oversampling ratio tau, n divided by s. It should, this tau is not it's a bad choice of notation. It's not the tau we care about in the previous result. So it's basically the oversampling ratio. And so on the left-hand side, we fix the target solution sparsity, and on the right-hand side, we fix the number of samples, but otherwise not much happens. And so these three plots are respectively for 5 times oversampling, oversampling by a factor 10, oversampling by a factor 20. And this is exactly what you expected from the theoretical bounds I've just detailed. When the oversampling ratio is much higher, you get much faster performance. Your problem is better conditioned. You have more samples, more data, more information, etc. It should be easier to solve, and it actually is easier to solve. There's a minor caveat here, which is that we're using the best restart scheme, and we're not including the cost of adaptation. If you include the cost of finding the best restart scheme, of course, the contrast between these curves is not as striking. So
what is the aspect ratio here? The matrix aspect?
I don't remember. I don't remember. I should check in the paper. Do I have it here? No. I'll find it in the paper later on. But so what's interesting, and that's my last numerical plot, is look at the total time. Again, it's for the best restart scheme, so it's ignoring the cost of the adaptation. But this is the total time it took to solve the problem up to precision 10 to the minus 2 for n equal to 100, 200, and 400. And what you can see here is that the total time to get to 2 digits is actually decreasing as the number of samples increases. And this is floating point complexity. It's everything all together. Arguably, it's in MATLAB, so these numbers are not perfectly reliable. It will be different if you run it on something serious. And more data, less work is controversial, but at least this is what we observe here, and this is sort of intuitive. So if Nati was in the room, we'd have an hour of discussion on this. He's not, so.
Nice for you to call it discussion.
Yeah, yes, but at least numerically here, this is what you observe, and you have to do a careful balance between what you gain by getting more samples in terms of iteration complexity and what you lose in terms of cost of each iteration because you have more samples. And if these two balance out in the right way, then in fact you can show that when you have more data, you have to do less work. But the question here is that the cost per iteration, the statement on iteration complexity is fairly generic because it depends on the optimal complexity bound, and there's only one such bound. The statement on the cost of each iteration is a bit different because it heavily depends on your choice of algorithm. And so, and on your implementation, and if you do subsampling, etc. So that number is something a lot more fungible, right? So agreeing on a total flop count is much harder than having a generic statement on iteration complexity. So that's why I'm not going to go any further, even though Natty is not here. But at least numerically, this is something you observe. And so I'm done. Just to conclude, so if you remember one thing from this talk is that sharpness is an assumption you can make safely because it holds almost generically, and it typically speeds up the convergence of optimization methods when you restart. Okay? Nothing else, that's the story. And for compressed sensing problems at least, it allows us to show that better condition recovery problems will be faster to solve. And we can make that explicit through the null space property. There are a couple of open problems. Adaptation in the generic holder case is still open. The cost of the grid search becomes much higher, and we don't have a good fix for that. And it would be nice. Restart looks a little bit artificial. Some people disagree. Some people find it a bit unnecessary in some sense. Ideally, especially because sharpness is a local property, you would want a method that adapts to the local sharpness of the problem. And we don't have such a method in the generic case, even though Vercock has a recent paper where they do something quite close in the strongly convex case. But that would be nice because then you'd get optimal behavior adapting at each iteration to the local sharpness coefficient, just as Nesterov's method, for example, does a simple line search adapting to the local smoothness of the gradient, and that has a massive numerical impact, right? So we don't have that yet, and it would help a lot. So that's it. I'm done. Thank you very much.
So we have time for questions.
Yes.
So on that second point, for algorithms for sharp problems without restart,
Yes.
so are there non-optimal algorithms, like just say gradient descent, that would automatically adapt to...
So gradient descent is an algorithm that restarts at each iteration, okay? Because it doesn't have memory. So restart only makes sense if you're talking about the method that has a little bit of memory. And typically this is one step, but one step is enough to make a difference. And what happens is that all the methods that reach optimal complexity must have some amount of memory. And in that case, restart makes a difference. Yes?
Is there a relationship between the sharpness condition and these KL inequalities?
Yeah, it's the same thing.
Exactly.
There's a long list of names, error bounds, sharpness, Lojasievicz, Kurdika.
KL needs differentiability or something.
Yes, but then you can broaden that to subanalytic function, it's enough. So, and then there's a recent paper by Mark Schmidt where they use the term Polyak-Lojasievicz. There's quadratic growth, the list goes on and on. And so the reason I'm using sharpness is because it's one word and it's more discriminative than the error bounds. That's it. And it's easier to spell than Lojasievicz. Yes. Yes?
So in your sharpness, you have this exponent, right?
Yes.
So could it be also some other arbitrary convex function instead of...
Yes, and there's a lot of that in Jérôme Bod's work, and it's a different approach to sharpness. They use a rectification argument. And so their way of characterizing sharpness is to say there is a function that is monotonic, blah, 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 and that turns my minimum into a sharp minimum that is actually an absolute value. And they quantify sharpness then in terms of that rectification function. So what you're looking for is exactly in Bod's paper. It's slightly more complex, but it allows them, I think, to get a broader set of results than what we do here. So absolutely.
Maybe one last question.
Yes.
You said you have similar result with the restricted eigenvalue condition.
Yes.
isn't it improving your result, your bound?
No, it's for a different problem. And so we can link the cone-restricted eigenvalue with the distance to infeasibility for the L1 feasibility problem. So it's a much more abstract problem. So we're not even discussing the same sparse recovery problem. So there's no immediate link between the two results, except that on one hand you have a complexity bound, and on the other you have a bound on statistical performance, and the two quantities turn out to be the same. But outside of that, everything is different. Yep. Thank you.